My name is Kenneth Smith, and this is the Chapter 2 lecture video titled, How Does the Computer Really Work? In this chapter, we're going to look a bit at how the computer actually works. I will tell you up front that in some cases, I thought the author went a little bit too in-depth or may have looked at some things that have not necessarily become popular. And therefore, we're going to kind of skim over the surface of a lot of these and really focus in on what's important in this chapter. So let's get started. Okay, basic nomenclature and components of a computer system. When we talk about a computer system, we're talking about typically some type of a box or something that houses the processing or the computer itself, along with a set of peripheral devices. And within the computer system itself, it has three main parts, typically something called a CPU or central processing unit. These are known as the brains of the computer. It's really what allows the computer to be able to look intelligent because it's making all those decisions as well as doing all of the mathematics and other types of functions that need to be done in order to give you the given results. There's also something called memory units, and memory units are used as temporary space to be able to hold value. So as the central processing unit is processing, it needs a kind of a working place where it can temporarily hold information as it's processing. These things are called memory units. And finally, we have the input-output units. And we'll talk more about input and output, but input is anytime we're trying to bring information into the computer, and output is when we're trying to send information out of the computer. So peripheral devices, they complement the computer to create a computer system. In most cases, a computer isn't complete without having these peripheral devices. And here the author talks about three types. So first of all, input transfers information from outside to the computer. We have output that transfers information from the computer to the outside. And then we have things that go in both directions, or bidirectional data transfer, which is input and output. So when we talk about input devices, we're talking about those devices that support us getting information into the computer, typically information that our programs can then process. So they can come in the form, as we see here, of keyboards. If you have a screen that has the ability to be able to touch, a lot of people are very familiar with this because of the phones and also with tablets, but you also see this touching of the screen available within computers themselves. And by the way, as we continue to go through this, one thing I should clear up is that really those phones and tablets are just mini computers in a lot of cases. So a lot of those things, when we talk about touching the screen, don't think of a computer as only that laptop or that desktop that you see there, but you can also think of it being the phone that you may carry if you have a smartphone. So, and they have programs as well. That's what you end up downloading from the App Store. So continuing on, we have microphones, which is what I'm using to send this information out to you, etc. So anything really that's allowing us to bring information in the computer, we can think of as input. Now, one of the things you see here are CDs and DVDs. So in this case, we'll be talking about the types that are read-only. So let's say, for instance, we go to a store and purchase a program that we then need to put into the computer. A lot of times that may come on a CD or DVD. So we could pop that right into the computer, and it then would allow us to put information in the computer, but it's not necessarily an output device in that case. They've made it in such a way that you can't rewrite or change the information that's stored there. We also can have output devices. Here are some of the most common ones. We see the printers and screens, by far the most popular ones, but you may also see maybe, as it says, audio devices and light devices. So by audio, if you have speakers connected so you can listen to it, if you're listening to my voice, you probably got some type of a speaker that's outputting that information. And then we have some that are bidirectional. Talks about discs, tapes, memory cards, flash drives, anything that's allowing us to go in both directions, both being able to save out to that drive and also being able to read off of that drive. Same thing with the output. Some devices, maybe we only send information out to, but we're really not going to read them in. When it talks about archival devices, just so you have an idea of what they're talking about, that would be a backup device where you're saving your information out in case something goes wrong. So in a real world situation, you probably think of that as more input output as opposed to output, because if something goes wrong and you need to get the information back, then you're going to use it as input. But anyways, hopefully you get the idea of the difference between an input and output device, as well as those bidirectional devices. Next, we're going to talk about something called von Neumann's model. And this isn't, once again, the concepts of how this works is somewhat important, but not the most important thing. Whether or not you understand this or not is not going to change whether or not you can program. So almost all computers, though, are based on this model of computing. The memory holds the instructions that comprise the computer program and all the necessary data values. And the control unit fetches the instructions and causes their execution. Oops, I'm sorry. I think I clicked on the wrong place. There we go. Now, von Neumann's model. The control unit fetches data from the memory to the CPU. So let's look real quick at how this happens. So first of all, when you write your program, you can think of your program as being executed in a serial fashion, meaning it's going to start at the top of your program and work its way all the way to the bottom of your program. And there are some times when we'll move around, but essentially it is processed in a sequential manner. So what happens is the control unit is going to grab each instruction. And our program, first of all, is loaded into the memory unit. We can think of it there, as well as our data. Now, by memory unit, there's more than one type of memory that is used on a computer, but we won't differentiate between those types. We'll just say it's all sitting somewhere in memory. So this control unit will grab an instruction and send it to the CPU. The CPU then does whatever processing it needs to do, and it'll send the results back, as well as the control unit also will at times pull data down that's necessary. And also, once that data is processed through the CPU, it's sent back to the memory unit. So the control unit controls the whole process of being able to say what's happening when. So it's going to go out, grab the instruction that's stored in memory, any data that's necessary, send that to the CPU. The CPU is going to process it, and then it gets sent back to the memory unit. This is all done because if you think about how central processing unit works, just from a simplistic standpoint, we can think of it as only being able to operate on one instruction at a time. Now, I know some of you may be really big on the computer side, know a bit more that nowadays a lot of ways that they're making computers run faster is by allowing them to have multiple cores so they can run more than one program at a time. Or more than one statement at a time, but they have to be written in a certain way. So let's not worry about that right now. We're going to think of our central processing unit as only being able to process one instruction at a time. So what's happening then is in between these, this control unit is taking each of those and it's moving information back and forth from the CPU, trying to be as efficient as possible to make sure that whatever the CPU needs, it's there when it's time for it to process. So reading through this, and that's essentially how this von Neumann model works. So let's just read through this the way that they talk about in the book. So the control unit fetches data from memory to the CPU. The CPU then performs the function specified by the function. So whatever it says to do, the CPU does. In this case, it says print 2, but you could be storing something in a place in memory. Any of those things would then end up causing it to be stored back into memory by the control unit. So you get a result of 2. The control unit saves results to memory and selects the next instruction. Result 2, and then the result will be saved back to memory. Now, if you're just printing a 2, it may or may not be saved depending on what you're actually doing with the 2, but if you're saving it to a variable, it's definitely going to be saved back to memory. The control unit saves results to memory and selects the next instruction. Which it would then, of course, send to the processor or CPU, which it does over and over again. So next we're going to talk about memory. What is memory? Memory is the place that we can temporarily store information. I say temporarily because typically with memory, we think of it as a way that it's going to be stored there, but once the power is no longer sent to that particular computer, it then goes away. So we'll need a more permanent method to be able to store it long term, but memory is very fast. So it's very fast and used to temporarily store information. So here we see the memory stores its contents in a sequence of numerical digits. And the way this works is that the author goes into something that's called the radix system, and essentially it's a numbering system. Typically, we use a numbering system base 10. So we go 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So those are 10 numbers. And then we get to 10, we move to another digit, and then we count 10 and we repeat. 10 has a 0 at the end with the 1. 11 then has the 0 changes to a 1 and so on. So it's a base of 10. The radix system essentially says that our symbols called digits carry consecutive values from 0 to r minus 1. So if we have a system that's based on 10, the digits become 0 through 9. If we had one that was we have things that are called octets or based on the number 8. So our numbering system would be between 0 and 7. Okay. And then once we move to 8, we would then have another digit there. So it would be a 1 and a 0. Sometimes these different numbering systems can be important because of the way that information is stored on a computer. We'll see that base 8 is important. We'll also see hexadecimal or base 16 can be important as well. But once again, because you know these numbering systems, is it going to make you are you going to be able to program if you really don't understand these? Yes, you would still be able to write effective programs without knowing them. But it is important to have some idea of what's going on, especially when we get to a radix of 1. So here it talks a little bit about the radix system. Here in base 10, you can see here that if it's 10, 10 to the 0 is a 1, 10 to the first gives us a 1, 0, 10 to the second is 100 or 1, 0, 0, 10 to the third gives us 1, 0, 0, 0. So you can see whatever number we have there, that's how many zeros we're going to have at the end. In this case, though, if we have a radix of 3, we'll see that's 3 to the 0, 3 to the first, 3 to the second, and 3 to the third. It's essentially saying how many numbers we can have within that particular numbering system if we're using a radix of 3. The thing that's important is this binary system. And also, as I said, octets and hexadecimals can be important. But the big one is, how does a computer actually store information? And information, you may have heard on a computer, is stored in a series of on and off states or zeros and ones. So when we talk about that on and off or zeros or ones, we can talk about it by using something called our binary numbering system. Now, once again, I don't want to get too detailed into this. You'll learn more about it as you go along. But essentially, the system is going to be able to store everything we want just using a series of zeros or ones. Zeros representing an off state, ones representing an on state. And here you see these numbers represented as binary. So we can see a 1 is represented as a 1. A 2 is represented as a 1 and a 0. A 3 is represented as a 1 and a 1. A 4 is represented as a 1, 0, 0. So every time we get to the R value, again, we have another place. So it becomes zeros and so on all the way down. Now, what does this mean? How is it working? I'm going to try to explain it to you very quickly. However, you'll probably learn about it in other classes you go along. You can also look in the book at it as well. But everything is based on this binary numbering system. And in this case, if we have just one bit, this is called a bit, one individual one, this would be 10 to the 0 power. So 10 to the 0 is a 1. I'm sorry, 2. I'm sorry. What am I talking about? We're talking about base 2. So 2 to the 0 power gives you a 1. So a 1 there ends up being considered on, a 0 would be considered a 0 or off. So if you had a 0 here, it would be considered a 0. It really makes more sense as we go down. So here, this first digit here would be 2 to the first. This would be 2 to the second. So if we have 2 to the first, that ends up being a 2. 2 to the 0 power is a 1. But since the 1 bit is on, so that would be 2 to the first, that gives us a 2. 2 to the 0 power is a 1, but it's off, so that gives us a 0. So you add those two together, you get a 2 plus a 0, which gives you a 2. When we go to a 3, which is represented as a 1 and a 1, hopefully this is where it really hits home. Since this is once again 2 to the first, this is 2 to the second, this is 2 to the 0, they're both turned on. So we take 2 to the second, 2 to the first, which is a 2, 2 to the 0, which is a 1. You simply add those digits together since they're both turned on, and we end up with a 3. Let's go ahead and do a couple more of these next two. When we get to this one, we now are at 2 to the second. So this is 2 to the 0, 2 to the first, and 2 to the second. 2 to the second is a 4. That's the only one that's turned on. So if you had a 4 plus a 0 plus a 0, that ends up giving us a decimal value of 4. And finally, the number 5 would be represented as 101. Why is that? Well, remember, this is 2 to the second, which is a 4. This is 2 to the first, which is a 2, but it's turned off, so we don't count it. We would X that out. And then we come over here to this first digit, which is 2 to the 0, which is a 1. So you add our 4 plus the 1, which gives us a 5. Had this other value been turned on, which is 2 more, it would then give us a 7. If we want the number 6, we'd have a 110. With each of these, we can only get one value back. So this is really the way that computers work. Internally, this is how things are stored. Computers can only store one of two states, either on or off. So all those fascinating things that you see computers doing, it's all being done internally by using this binary numbering system. Next, we're going to talk about addresses. As it says, consecutive natural numbers are used as addresses to access contents from the memory. So as information is being stored to memory, it has to have some way of being able to find it. Much like in our society, if a mailman is out delivering packages, they need a way of being able to find each individual house so they can give you the correct mail. So they use an address. So they go out and they have a street along with a number which corresponds to a house number. And then they have a city, usually a state, and a zip code, and that's enough to get your mail to you. In this case, computers do sort of the same thing, but they just have a number for each address in memory. So maybe the first address is number 1, the next one is number 2, the next one is number 3, and so on. So it's just a way of being able to find information that's stored in memory. It just has an address to it. So here's showing memory, and maybe this is the address of that piece of memory. And this is the data that's stored in this consecutive memory. Okay, so the first one may have a 0, and then it may be a 1, a 0, 1, and each of these is going up by 1. So you have this long string of bits, which it then can interpret into either a number or a character, depending on what you're actually storing there. And we'll see, we're going to talk a little bit later about numbers and characters. But remember, everything that we're storing when we talk about those is being stored in memory as 0s and 1s. And that's the reason we took a while to talk about this. And here's an example address in Bart's house. I think I talked enough about the addresses. But let's read through this. It refers to cells that hold 8 bits called bytes. One of the things that's important, I mentioned octets, is this whole idea of 8. And what happens is within a computer system, we typically look at it as being able to store a byte. Now, why do we look at this byte? Well, typically we think of it as being able to store one character. So a character can be stored within 8 bits, and each character has a number associated with it. So it can be grouped into larger strings, can be accessed in an arbitrary order, referred to as random access memory or RAM. So when we're talking about storing this information out, we group these strings into, they can be grouped into larger strings, so it would take up consecutive or contiguous spots in memory, and it can be accessed in any order because we can go back and say we want to go to this specific address and grab just that information. We don't have to grab information in the order in which it was stored out. We can grab it randomly, hence the term random access memory, or you'll hear the acronym of RAM. Scales of magnitude. Here, mass storage devices are equally measured using units based on the power of 10. So what we do is we'll see here, as they say, it's customary to equate 2 to the 10th as 1,000 because it's very close to 1,000, but it really comes out to 1,024. In a lot of cases, we'll find that there's a little bit different amounts than what we say. But that's fine. It's very close and it's close enough. So when we start talking about scales of magnitude, we're really looking at how do we define quantities on a computer system. There are precise numbers for sizes can be stated using multiples of the power of 2, but a lot of times we use multiples of 10 to address those just because it's easier and it's close enough. So here we can see units and their sizes, and there are names based on 2, but these typically aren't used. And you can look at those and you'll say a lot of those you may have never seen before. But typically we go ahead and use those sizes that are close enough. When we say megabyte, we're talking about a million bits. When we talk about a gigabyte, a million bytes. When we talk about a gigabyte, we're talking about a billion bytes, and we talk about a terabyte, we're talking about a trillion bytes. Each of these you'll find used in different situations. For instance, when we talk about how much memory do I have on my computer system, typically you're probably going to have a certain amount of gigabytes. When you start talking about, well, how much hard drive space do I have, a lot of times that leaves the gigabyte space and moves into more the terabyte space. And these things are going up all the time as we continue to make things faster and larger for less cost. We'll find that some of these things are getting larger and larger. In addition to that, we find that as these things are getting larger and larger, we're starting to store more and more information out. So instruction execution. Instructions are executed in time phases. This gets a little bit tricky how the author talks about it, so let me see if I can simplify it a bit. What happens is there's something called a clock cycle. So as our computer system is processing information, everything is timed. That way, when one process is done, another one is ready to go. So everything is timed in such a way that there are these things called clock cycles. And things happen during a clock cycle. Typically, a lot of times you can find that an instruction is completed within a certain amount of clock cycles. Maybe it's done in one clock cycle, but as it says on this bottom step, sometimes it may require multiple clock cycles or time steps. And that's all this is talking about, is that as instructions are being executed, they're being executed based on these time cycles or this clock. And here it talks a little bit about the different speeds for the clock. Once again, not the most important thing to talk about. Here you see, and they had a statistic from 2013. Computers operate on a clock that's between 2 gigahertz and 10 hertz. THz hertz. I'm not sure what T is. I'd have to look that up again. Probably terahertz. But essentially, when you're talking about a home computer, you'll find that today even that they're probably still up around 3-point-something gigahertz. What happened is over time they started changing things a bit, that instead of just making computers faster, this clock faster, instead what they've done is they've made it so that they do something called multi-threading processes where they can run more than one instruction at a time. So suddenly you start hearing about multiple cores. You can buy a 8-core processor. So that means it has 8 cores that can all end up running at the same time within a single CPU. Once again, far beyond what you need for this first class. But since they talk a bit about this, I just thought I would let you know what's important there. Instruction execution. Here it talks about instruction execution. They can be measured in million instructions per second, billion instructions per second. If you're doing floating point operation, that means you're doing decimal numbers. How many flops can it do per second? Or floating point operations per second. And TREPS, which is trillion edges per second. And as it says, a new 2011 measure. So as these things get faster, we keep finding that we need new ways of being able to measure them. And you'll see these terms occasionally, but once again, it's good to know because you have some idea of how fast maybe that particular computer is. But as a programmer, you really don't have to worry about this at this point. Bit sequences. The interpretation of a bit sequence meaning depends on the usage of the sequence. A bit sequence can be interpreted as an instruction, numerical, logical control, or program flow. Bit sequences can also represent data, integers, float, or real, as well as characters. So what do these things mean? Well, an integer is an integer number, a number without a decimal point. It's just a whole number, as you probably learned in math classes. A float, a real number, is one that can include a decimal point, and a character would be really anything that you can see on your keyboard that you can type, and even things beyond that. So data types, hardware. So integer represents a numerical value in radix 2. So remember, that's our binary numbering system, those zeros or ones. And it says length limited by length of its string representation. So you'll see that in many languages, you'll have something, maybe a regular type and a long type. And they're defined as being able to hold numbers up to a certain value. The purpose for that is that you may have to define this up front. And by doing that, it then only uses up the amount of space that you need. That way, saving memory. Because sometimes you have programs that may be temporarily storing out millions of pieces of data. So by picking which one of these you're actually using can make a difference in how much memory you have available. We also have floating or real numbers, though they're represented in scientific format as x times 2 to the y. Once again, you don't have to worry about this. It's just talking about how much space this ends up taking up in memory based on the number that you have. And then we have character types. Not sure why that went backwards. I think I had my mouse in the wrong place again. It keeps going to that bottom left, and I think I was clicking on this item down here. But a character is 1 to 4 bytes. 1 to 4 bytes can come as a single character as part of a string of characters. What happens though is some of these numbers that are being thrown out can differ from language to language. So don't worry and think that these are always true. Some languages handle things differently than other languages. The character 9 is stored differently than the integer 9. One of the things we'll talk about later when we really start getting into the language, which is going to happen next chapter, is that we can have something that's stored as a character that can be a numeric, as well as something that's stored as an integer in this case that's numeric, or a number. It could also be a floating point. The difference is if we do something that's stored as a character, as we see here, we can't do arithmetic with it. If it's stored as a character, it's going to treat it as if it's text. We'd have to convert it into a numeric 9. And then once it's numeric 9, we could then add, multiply, divide it, or do other arithmetic operations to that number. Interpreter process and Ruby. Programs express algorithms using a sequence of statements. However, we can't use those sequence of statements in our program. It's not programming code, it's an algorithm. It's something that's in English. What happens though is, as it says here, cannot be executed by a computer because they are not written in binary digits. When a computer processes information, it's always processing something called machine code. So what happens is whenever we have a computer system, we have to some way or another get this information or these programming steps that we want it to process into machine code. And this is done via using something called a compiler or an interpreter. So there are two different methods that are used in order to do this. So first of all, our computer programming programs need to be written into a language that this compiler or interpreter are able to understand, so they can then convert it into machine code, which is what the computer needs. And that's what we're about to talk about, these two different things, because they're a bit different. They also throw a third one in there, a mix of partial compilation to an intermediate code. We'll talk about that as well. So first of all, let's go ahead and talk about compilation. After we write our program, if we're using a language that does compilation or compiles it, it takes the code we have, we hit a button or some other method, and it compiles it all the way down to what's known as an executable. Most of you have probably used Windows before, so this would be the equivalent of taking a program and making it into an exe file, one that has an extension of .exe, which we typically think of as an executable file. When we compile it, we only have to do that once. Then after that, we can run our program over and over again and never have to compile it again, because the compiler takes it, turns into machine code, and then that exe file is machine code that we can then run over and over again. Another method is something called an interpreter interpretation. This method, instead of taking your entire program and turning it into machine code right away, instead what it does is every time you run your program, each of those lines is going to be interpreted one after the other. So it's going to be interpreted at runtime. So every time you run it, it's going to be recompiled in a sense, or changed into that machine code that's necessary for the computer. There are advantages and disadvantages to both of those. Some more modern languages move to something called more of a mix, where they compile down to intermediary code. So what that means is, instead of taking our programming code and turning it into machine code right away, they have this intermediary code that they compile to. A couple languages I'll talk about that do that. First of all, Java does that. And one of the reasons Java did that is Java, as a programming language, said, we want to be able to run on not just one system. We want to be able to have you create your Java program and run it on anything. So that has something called a Java virtual machine. So what that means is I could then write my Java program on a desktop, and then I could also take that program, and as long as there's a Java virtual machine available for my phone, I would then be able to run it on my phone. Same thing as if I had a different operating system. Maybe I'm using a Mac. As long as there's a Java virtual machine, I would be able to run it on the Mac. Same thing with Linux. So being able to write your program once and run it on many different systems, which does work. Some of the things that you do encounter, though, are things such as, what happens all of a sudden if I run this on a phone? My screen size is different. So there are typically some things you may have to go back and change, but that's what it does. But that also means you need this Java virtual machine. So it compiles it down to intermediary code, but when you run it, then this Java virtual machine still has to be out there in order to run. That's why a lot of times you find on your computer you may have to download Java in order to get something to run. Another language that does that are these things called .NET languages. And Microsoft, once again, just like Java, decided to make it so it goes down to an intermediary code. Their idea was more this, because they're invested in Windows. They want Windows to stick around. So their programming languages typically compile down to Windows. But what their scheme was that we're going to be able to make it so that you can program in any of these different languages. Now, typically, different languages are not compatible with one another. But what they wanted to do was they wanted you to be able to use any of these different languages that are, as long as they use this .NET methodology, they'll compile down to the same set of intermediary code. So one person might use Visual Basic, another person might use C#, another person might use some other .NET language. And essentially, it still all comes down to the same core of code. So then you can intermix these things more easily and make them function together. But once again, that means then within Windows, there's something you have to download, which does come with Windows automatically now, which does that last piece of compilation at runtime when you're ready to run the program. In the case though of Windows, it has a lot of libraries, so it gets rid of some of the duplication of having to have these libraries in your code. They're just part of your operating system. Enough of that though. I know I went overboard there, but just to give you an idea of how these things work. So this talks about compilation. I've talked enough about this. I'm going to skip these slides. Oh, one thing I didn't miss, there's two ways for interpretation, an interactive mode and a batch mode. Interactive mode means that as you're using a program is being interpreted. Batch mode would mean that when you run it, it's going to go ahead and interpret it, and then you'll be able to run your programs. So this talks a little bit about that. See, the entire program is prepared and stored in one file. And then, of course, as you're running it, becomes input for the interpreter that analyzes and executes each statement. So you're essentially telling it to run it in a batch mode. So in summary, a computer system includes a computer and peripheral devices of various types. We talked about the different types that you can have. You have input devices, output devices, input-output devices, and all of those things help to give you further capabilities with your computer system itself. You have the CPU, which are the brains of the computer. The CPU, or central processing unit, is really the part that does all of the processing and really makes it so that your programs are able to function, and it really does all the work. Just to give you an example of central processing units, which I didn't do, the two big ones that you'll probably hear are Intel and AMD on desktop computers, but you do have other CPUs as well. Phones use different ones depending on the company that they decide to go with. We talked about the von Neumann model, where we have the control unit, which is sending information to the central processing unit, working in conjunction with memory. We talked about memory that is used to temporarily store information. Remember, with memory, it is volatile, so when you turn off the computer, it goes away. But it's also very fast. That's the reason we have it and that we use it. In a matter of fact, it's many times faster than going out to a drive. That's why we have memory that's volatile, but then we use our drives to permanently store information. The computer uses strings of numbers or addresses to access contents in the memory so that it knows how to go find that information. We talked about timing, the fact that there's a timing for instructions, which keeps everything in sync. So as we're processing information, we can then make sure that things proceed in an efficient manner. All data are stored in binary form, those zeros and ones we talked about, but their interpretation depends on their usage. And programs are either compiled or interpreted. And that brings us to the end. Thank you for listening.